Welcome back. In this little tutorial, I want to talk about a concept that sometimes, while useful, can easily become controversial if misused. You will find a reference to some of these concepts discussed in this tutorial in the chapter 2 of the book by Dr. Bishop. And to understand the utility of this concept, that is conjugate priors, it would be a good idea to recall what we had done in part 5 of this series. We had formulated the posterior predictive distribution expression as the expectation of likelihood random variable in which the sampling distribution is the posterior distribution. Since for continuous random variables the expectation is computed using integrals, I had mentioned that it is the thorny part in this elegant story of Bayesian approaches to modeling. As such, the posterior predictive formulation is not the only place where there is a need to compute the integrals. It also appears in the posterior distribution formulation and is shown using the symbol n. The denominator in the posterior distribution is the challenging part, as it expands to the integral that looks like this. Unfortunately, the denominator of the posterior distribution is known by various names. It is known as normalizing constant, evidence, marginal likelihood, and partition function. Partition function is the strangest out of them and is generally used in the literature from the field of statistical mechanics. At the moment, I don't want to talk about it, why it is called partition function. Maybe in some other tutorial. I have a strong belief that not using consistent symbols, notations, and terminology is one of the elements that makes the life of student very difficult. Anyways, it is what it is. We can't change or solve this aspect. But at least now, when you will read other articles and papers, you would be aware of these terms associated with the denominator of the posterior distribution. Bottom line is that this normalizing constant, the denominator, is to be computed if we want to have a posterior probability distribution. Now, whenever you encounter integrals, the first approach to compute it should be to figure out if there is a possibility of having a function that computes it. In other words, we look for closed form functional expression to compute it instead of using numerical integration approaches. And this brings us to appreciate the big idea behind the topic of our tutorial today. The idea is that if somehow we know the functional form of our posterior distribution, then maybe we have a chance of having a closed form expression to compute its normalizing constant. If it is the first time you're hearing about this, then it will sound strange. So let me give you a very simple example of what it means. This is a clipping from the article on Gaussian function from Wikipedia. Here the expression you see is the closed form expression for computing the normalizing constant for Gaussian function. If we know the functional form of our posterior, then we have a shot at computing its normalizing constant using a closed form expression that some mathematician and statistician have already derived for the rest of us. Now the natural question here is to ask what or who determines the functional form of the posterior. And clearly it has to be these two, the likelihood and the prior, at least here in this formulation. That is the product of likelihood and the prior. So if you can choose the prior distribution function for a given likelihood function in such a way that you would know what would be the posterior function, then we would be in better situation. Of course, it is very few combinations or configurations in which the product of likelihood and prior will result in a known posterior functional form. The priors that for a given likelihood function give us known posterior functions are called conjugate priors. It is like an arranged marriage if you think about it. Now, whether this marriage is made in heaven or forced upon us is a different matter. Let's talk about it towards the end of the tutorial. It's not as bad as it sounds. For now, I will show you some very well-known conjugate priors for the likelihood functions. Here, the likelihood is the normal distribution where we have a fixed or known variance. And the model parameter is the mean or mu, essentially the parameter that we want to estimate. And this clipping from Wikipedia is showing that in this case, it would be wise to use the normal distribution for the prior or on mean. And because of this marriage, you would have a closed form expression for the parameters of your posterior distribution. Some very capable mathematician has already simplified and derived it for you. And by the way, not only for the posterior distribution, but they have done so for the posterior predictive distribution as well. And of course, this is not the only scenario for which you have access to the closed form final expression of the parameters of posterior and posterior predictive distributions. This is another scenario where instead of thinking in terms of variance, you are using precision. Precision is the inverse of variance. This scenario is interesting as well. Here you are considering that you know the mean but are interested in getting the posterior distribution of variance. The conjugate prior in this case will be the inverse gamma distribution. And by the way, it's not like that you only have one possible conjugate prior for the given likelihood function. This entry here is showing that for a known mean, and when the parameter to estimate is variance, you can also choose scaled inverse chi-squared distribution. And note, in this case, and the previous one as well, the posterior predictive distribution is the student distribution. And the one that I really want to show you is the configuration when we have a known mu and the parameter to estimate is precision. Again, recall, precision is the inverse of variance. And now I get to give you some justification of doing things that I described in part 2 of this series. If you have seen this tutorial, you should remember that we had expressed our target random variables in few different ways. And we had finalized on the form where precision was used using symbol beta instead of variance. I had mentioned that I am doing so because the book uses this notation, but I also said that there is a reason behind it. And the reason is that for precision, the conjugate prior is the gamma distribution. As such, you saw that we do have a conjugate prior for variance, which is inverse gamma. But quite often, we like to work with a gamma function rather than an inverse gamma function. Here are conjugate priors for multivariate normal distributions. And the one that I have highlighted is the case for precision matrix. So quite similar story to that of a precision and gamma distribution. Here, when you are in a multi-dimensional realm, you are going to be dealing with covariance matrices or precision matrices. When you will use precision matrix, then the conjugate prior is going to be a distribution known as Wishart distribution. And if you decided to use a covariance matrix, then you will be dealing with the inverse Wishart distribution. This table that I have here is taken from the Wikipedia's page on conjugate priors. So you already have functional form for quite many configurations. I have only described to you the continuous random variables for now, the priors and the likelihood function which are used for continuous variables, but the Wikipedia page also talks about the discrete random variable case as well. And this brings us to the end of our little tutorial. But I did promise to talk about arranged marriages, so here are a few words on this comparison. In the Western world, arranged marriages are frowned upon. But the fact remains that even today, a significant number of people in India have arranged marriages. And I can tell you that it's not like they all fail or all couples are unhappy. And more importantly, arranged marriages are not looked down upon. You see, what is weird in one part of the world is a norm in another part. It happens with many other things. That said, marriages, whether they are arranged or are love marriages, are never perfect. In India, marriages that are not arranged are called love marriages. You may find the term itself quite strange because in the Western world, why are you marrying if it is not for love? But more importantly, marriages are not perfect and neither are our models. So, if the marriage of likelihood and prior works, provided the model is not completely absurd and or is not forced upon, it would be unwise to ignore this aspect. I have mentioned this earlier in many other tutorials that keeping an eye on the computational cost is as important as modeling itself. You see, if you have the most perfect model in terms of accuracy, but it is computationally so expensive that you can't even deploy it, then it is as useless as having the worst model or having no model at all. Conjugate priors enable the possibilities of reduced computational needs, and perhaps they do so at the cost of not so accurate model. As a scientist or an engineer or a statistician, you have to learn to balance both the requirements for accuracy and computational costs. And of course, by all means, invent methods that are good at answering both of these requirements. That said, this concept of conjugate prior is applicable only in limited scenarios, and therefore we must explore the alternatives and evaluate their respective pros and cons. As part of this series, I do plan to talk about these methods of inference, and this is where I will end this little tutorial of ours. I hope this was helpful and useful. Let me know in comments if you need more clarifications and or have questions. See you in another tutorial. Goodbye.